We're going to use everything we've known, asymptotes, intercepts, first and second derivatives, to try to sketch a polynomial function. Now, you can sketch functions using a graphing calculator, but sometimes they overlook details that are very important. Depending on the scale you use, you may totally miss a maximum or a minimum. The calculus won't miss anything. So we're going to carefully go through and see what we need here. Now, I tend to do asymptotes first because they don't require calculus, the derivatives. This is a polynomial. It doesn't have any asymptotes, so we can skip that part. So let's go look at the first derivative. F prime of x is equal to 4x to the third plus 12x squared. Relative max and min occur when the first derivative equals 0. So if I set that equal to 0, I need to factor. So I can pull out a 4x squared. I'm left with x plus 3. Set each piece equal to 0. 4x squared equal to 0 gives me x equal to 0. X plus 3 equal to 0 gives me x equal to negative 3. So those are the numbers we put on our number line. This is the most efficient way to determine if we do indeed have a max or a min at either of those places. So put it on the number line, negative 3 and 0, and we'll do test points. Let's say down here, let's look at f prime at negative 4. I put in negative 4 squared, it becomes positive. 4 times positive gives me a positive. Negative 4 plus 3 is negative. So my first derivative here, if I multiply positive times negative, is a negative on that interval. Let's look in here, say f prime at negative 1. Negative 1 squared is a positive, times 4, this piece is still positive. Negative 1 plus 3 is positive. Multiply those two together, I get a positive for the first derivative. Past 1, let's just look at f prime at 1. 4 times 1 is positive. 1 plus 3 is positive, so I have a positive. Now the first derivative tells me increase and decrease. So this tells me that my function f is decreasing on this interval and then increasing on this interval, and after it hits this place where the first derivative is 0, horizontal tangent, horizontal 0 slope, it still increases after that. So nothing particular that I can see happens at x equal to 0, but at x equal to negative 3, the function decreases to that point and then increases and increases. So this at x equals negative 3, f has a relative minimum. So now we'll go to the second derivative and see if that gives us some information about what might happen at 0. So let's look at f double prime of x. 3 fours are 12x squared plus 2 12s are 24x. Again, I need to factor, set it equal to 0. I can pull out 12x. I'm left with x plus 2. Set each piece equal to 0, I get x equal to 0 and x equal to negative 2 as the places of interest from my second derivative. So 0 was a place of interest, was a critical number for both derivatives. So let's look at the number line here. Put negative 2 and 0. Test point for the second derivative, say negative 3. 12 times negative 3 is negative. Negative 3 plus 2 is a negative. So my second derivative is positive, less than negative 2. Let's try f double prime at negative 1. 12 times negative 1 is a negative. Negative 1 plus 2 is a positive. Multiply those two, I get a negative. And f double prime at 1. 12 times 1 is a positive, 1 plus 2 is a positive, so I have a positive. So that gives me my second derivative, and it tells me concavity. So the function f is concave up here, and then concave down, and then it turns again and becomes concave up. Since concavity changed at both of these points, -2 and 0, what I have there are inflection points at -2 and 0. Now, sometimes the question may ask, where do you have relative max and min? Relative minimum at x equals -3, inflection point at x equals -2, and x equals 0, and that may be all you need. But we want to sketch, and if you want to sketch accurately, this is not quite enough. We do need some data points. So we have to go back and try to figure out maybe what some of our values are for this function. But I think, let's just see in general what this one looks like. What is it? X and f, the function f. This says it decreases to x equal to -3, and then increases to 0, and then increases again. So let's say -3 is here. This has it concave up to the left of -2, and something happens at 0. So I decrease till I get to -3, and I don't know really where this is. I'm just going to put some numbers in. Tell you what, let's plug in 0. Oh, look, at 0 you get 0. So if it decreases to -3 and increases to 0, it's going to go down here. So let's go down to -3. That's where our minimum is. Back up, and at -2, concavity changes. Let's do a little sketch first. Goes up at 0 and then up again. But we need to take into account the concavity. Concavity changes at -2, so wherever this point is, my concavity needs to turn down until I get to 0. So this is going to begin to curve down a little bit there. Get to 0, and then it begins to curve up after that. Let me make this a little bit curvier. Concave up to this point, concave down, and then at 0 it turns to be concave up again. So this is about what the graph looked like. I checked out one point. I didn't want to plug in -3 to the 4th power. So this is in general what this graph is going to look like. We're going to try to sketch a polynomial function, but this time we want to use the graph of the first derivative and the graph of the second derivative to sketch the function f. So let's think first, what does the graph of the first derivative tell us? Well, when I have the first derivative, I think in terms of is it positive, negative, or 0. So here at 0, my derivative is equal to 0, and since f prime equals 0 at that point, that gives me a possible max or min, possible relative extremum. But notice that all of these other numbers, this whole other graph, is below the axis, so f prime is negative. F prime negative tells me f decreases. So my original function f is going to be decreasing everywhere. Let's start off with an f that's decreasing everywhere. And if it's decreasing everywhere, something happens at 0, but it's not a max or min because it's negative everywhere else. It does not change from increasing to decreasing. So our graph of our function f is always going to be decreasing. Let's look at f double prime. F double prime tells us concavity. My f double prime here is positive. When f double prime is greater than 0, the function is concave up. When f double prime is greater than 0, concave up. When it's negative, the function is concave down. At 0, we have possible inflection points, and it turns out we do have inflection points because concavity changes. So we have two inflection points at 0 and at 4. So we have a graph that decreases, and I kind of like it going through 0 on both of them, so let's go through 0 here. The function is always decreasing, and it's concave up to the left of 0. So our function decreases, but it's going to be concave up. After 0, from 0 to 4, our graph is concave down, but it's continuing to decrease. But when I get to 4, it changes to concave up. So let's say this is 4, and down here somewhere, we're going to be concave down to that point. And then it's going to change to concave up, but it has to continue to decrease. So let's go back and look and see if this makes any sense with it all up here. Function always decreases. It's concave up to the left. It's got a 0 here, so this should be a little bit flatter in the middle here so that we have a horizontal tangent. That is a point of inflection. It becomes concave down, another point of inflection, and concave up. And of course, this is a polynomial function, so it's all supposed to be a whole lot smoother than my little bumps in here. But this is how you can estimate a possible graph for a function using information from the first and second derivative graphs, just like we can from the first and second derivative functions when we know exactly what the numbers are. Let's look at a function that involves the product of an exponential function and a polynomial. X is a polynomial, x to the first. So this section is sketching exponential functions, but they can be connected with other things. So of course it's more complicated than just sketching f of x equals e to the x. Because of that, we use the calculus, we use derivatives, asymptotes, everything that we've learned to get an accurate sketch of this function. Probably for this particular function, much more accurate than you would get if you decided to try to use a graphing calculator, because some of the details are pretty close together. So, since we know an exponential function has an asymptote, usually let's look for asymptotes first. So if we want to do the vertical asymptote, usually what you look for is if there's perhaps a denominator, something where your function cannot exist that will stop it at a place. We don't have a denominator here, so we'll have to go look at the definition of vertical asymptote, which means guess what it might be and take the limit as x gets close to that number. There's really no problem with any numbers here, positive, negative, zeros, so there is no vertical asymptote. None. If we try to take a limit, we have to approach a number. X approaches 0, x approaches 2. We just get numbers for that. So let's look at horizontal, because that's the asymptote that we usually have with an exponential function. And to determine horizontal asymptotes, you really take the limit as x approaches infinity or negative infinity. So let's approach infinity of this function. And if we take really big numbers and plug them in, x is 1,000, e to the x is way bigger, so the limit as x gets bigger just keeps getting bigger. Since it doesn't equal a number, there's no horizontal asymptote as x goes to positive infinity. So let's look at the limit as x goes to negative infinity. Now, I want to do a little figuring with this. When x goes to negative infinity, let's think of a large negative number. For an exponential, I'm just going to think of 100 as being large for now. So if I plug in x equal to negative 100 and e to the negative 100, well, a negative exponent can be written in the denominator. And if you look at it this way, this denominator is huge, and the numerator stays negative 100. So a fraction whose denominator gets bigger and bigger and bigger and bigger, while the numerator does not change, that goes to 0. So the limit as the x approaches negative infinity is equal to 0, and that tells me that I have a horizontal asymptote at y equal to 0. So that's my horizontal asymptote, and it's on the left because x was approaching negative infinity. So, got through the asymptotes with just a couple limits. Now we have to go back and sketch using derivatives. So we need to get the first derivative. And to get f prime of x, I'm going to have to use product rule because it is x times e to the x. Let's give ourselves a little room here and use the product rule on this function for the derivative. Product rule is first, derivative of the second plus second derivative of the first. So first is x, derivative of the second is e to the x, plus second is e to the x times derivative of the first is 1. To simplify that, I'll factor out the e to the x, and it gives me e to the x times x plus 1. Now for the first derivative, it tells us relative max and min if we set this equal to 0 and test the critical numbers that we get. I look at each piece to find a critical number. E to the x is always positive. E to the first, e to the 0, e to the negative 10. Positive numbers. X plus 1 equal to 0 gives me x equal to negative 1. So the only critical number that we have is x equal to negative 1. That's the only thing that goes on the number line. I do a test point on either side. If I have 0, I put it into the first derivative. I find e to the 0 is 1, that's positive. 0 plus 1 is positive, it's positive on that side. My first derivative, f prime, is positive. If I put in, I just did that backwards. Back up, 0 is not over here. So we need to change these to here. Remember, 0 is to the right of negative 1. Let's go back and pick up an actual number that's to the left of negative 1. Let's say negative 2. That'd be a little bit easier to look at. So if I plug in negative 2, e to the negative 2, still positive. Because e to anything is positive. Negative 2 plus 1 is negative 1. So that's a negative. Multiply those two, I get a negative. So I have that my function f decreases and then increases. First derivative is negative, the function f decreases. First derivative is positive, the function increases. So I do know where the function increases and decreases, and that tells me now that I have a minimum at negative 1, a relative minimum. Relative min at x equal to negative 1. Okay. Let's see what we have to do with the second derivative. I've taken the first derivative, so from there I need to take the second derivative. So let me leave this part up for a bit. F double prime of x. Let me back this up some. F double prime of x. I'm going to take the derivative from this point because I have an e to the x times x plus 1, and the pattern is similar to when I took the first derivative using the product rule. I write down first e to the x times derivative of the second, which is 1, plus the second times derivative of the first, derivative of e to the x is e to the x. Now, I'm going to factor out e to the x. I have one here, and then here's a plus, and there's another one. So I can pull it in front. I'm left with 1 plus x plus 1. And I could put the x plus 1 in parentheses, but I don't really need to. So what I have for my second derivative is e to the x times x plus 2. And again, the e to the x does not give me a critical number when I set it equal to 0, but this part gives me x equal to -2, so I put -2 on my number line. And I'm testing second derivatives, so I can't plug in -2 this time. Let's plug in -3 and see what we get. E to the -3 is positive. -3 plus 2 is negative. So when I multiply those two together, my second derivative is negative. Let's go to the right of -2. I like 0 for this one. I like 0. E to the 0 is 1, that's positive. 0 plus 2 is 2, that's positive. Two positives multiply to give me a positive. Second derivative tells me concavity. So I know that my original function f here, second derivative negative, is concave down. Positive here means the function's concave up. So I have a relative min at x equal to 1. My concavity changes, so this is a point of inflection. Let's put in some more information right back up here. I have inflection point at x equal to -2, and then my concave down from -infinity to -2, concave up from -2 to infinity. Okay. So I have about all the information I can. Let's see if we can sketch that. Let's remove the first derivative and the second derivative. Now, I did not mention my increase and decrease up here when I set a relative minimum. So let's remember that it goes down to x equal to -1 and then back up. Now, when I sketch, since I'm actually going to sketch, let's see how accurate we can get. Let's look at some numbers. I'm working with -1 and -2 as places where things happen. It's always a good idea, if possible, to get maybe an intercept. And for this function, if I find f of 0, that's easy to do. 0 times e to 0 is 1, 0 times 1 is 0. Now I want to find where my value of my function is at -1. So if I put in -1, I have -1 e to the -1. Okay, well, let's call this scratch work. I have -1, and e to the -1 goes to the denominator. So that's -1 over e. E is about 2.7. I'm going to get that fairly exact because when I put in -2, it may not be very different. And if you use -1 over e, don't use 2.7. Put in e to the first, so you'll be much more accurate. And this number turns out to be approximately -0.37. Okay. I usually estimate it about a third, but it's actually 0.37 instead of 0.33. So this is approximately -0.37. F of -2 would be -2 times e to the -2. So let's figure out what that one's going to be. That will be -2 over e squared. And that is a little bit more complicated. So with calculator for that one, we find out that that is about -0.27. So with -1 over e and -2 over e squared, you don't really want them both to round to 0.3. This could be 0.4 and this, excuse me, and this could be 0.3. And I have three important points: an intercept, an inflection point, and a relative minimum. Let's see what the graph looks like. x, and this is my function f. So I'm interested in -1 and -2, and I know f of 0 is 0. F of -1 is -0.37, so let's just call this -0.27, and we'll call this -0.37, not to scale. At -1, my -0.37 is a minimum. So that means it has to go down to that point and back up. At -2, the value is -0.27. That is a point of inflection. So as it goes down, my concavity has to change. It's concave down until I get to -2, and then it turns to become concave up. But it's decreasing. So this is one of those odd things with concave down. The function is decreasing, but it's cupping down till I get to -2, and then it turns and cups up until I keep going. So it has a little bit of an angle, not an angle, a funny downward sloping curve here until I get to -2, and then from there on, it's concave up, and this is my minimum. There's a lot of little detail in this problem, and in some cases, you only need to know where things are. You don't actually have to sketch. But it helps to see what a sketch looks like when you have all this information that you need a picture in your head. So this is what this function looks like using all the information that we need. Oh, I totally ignored my asymptote. Let's back up. I was looking at all of this and forgot I have an asymptote. This doesn't even go up here. All right, let's try this again. The downward slope looks like that. Oh, make it bigger. There we go. Oh, I like that better. Don't forget the asymptotes. So it does have an asymptote on the left at y equal to 0. So as it comes back, it goes down like that and then curves. And this is where concavity changes at -2. Be careful with your graphing. In this segment, we'll look at sketching logarithmic functions, but it's also possible that you'll see questions that have a variety of functions, exponential and polynomials, just because when it's the last lesson, tends to be a capstone with everything coming together. So let's look at this one first, which is one we've looked at in great detail with first and second derivatives already. So the main thing I want to talk about here is the part about asymptotes. We found asymptotes with exponential functions. We had no asymptotes with polynomial functions. But let's think about what we have here. We have to have x greater than 0 because of natural log x. You cannot put in 0. You cannot put in negatives. So the natural log of x function by itself is graphed like this. That's what y equals ln x looks like. So it has a vertical asymptote as x gets close to 0 on the right-hand side. Y values go towards -infinity. So for this, I would say, okay, I'm betting that for this question, x equal to 0 is a vertical asymptote. Now, x doesn't equal 0, which is exactly right, because the function never has a value at a vertical asymptote. But let's see what this multiplier of x is going to do. As we look at the limit, as x approaches 0 on the right, if I pick numbers for x, this is 1, for y equals ln x. Let's say 0.5. If I do x ln x at 0.5, I'll have 0.5 multiplied by the natural log of 0.5. Well, this is some negative number. I'll say small negative for here. This is a positive number. I'm multiplying them together. I get a small negative number. so that for the function I'm looking at, as I get close to zero, I'll have a number, say here, small negative y with a small fraction x. Let's pick a smaller one. Let's look at 0.1. This is a bigger negative number because remember the graph got lower as we got close to zero, and this is just 0.1. So if I have a bigger negative number and multiplied by 0.1, I actually end up with a smaller negative number because 0.1 is much smaller than 0.5. So my numbers are going this way. When you get very, very close to zero, you can't plug in zero. What you have is a hole. There is a hole in this graph at x equal to 0. There is not an asymptote. No vertical asymptote. But you really can't tell the difference with natural log combination functions like this unless you actually set up like a little table and plug your numbers in. So check those, see what you'll get, you'll see what happens. This particular graph has no vertical asymptote. It has a hole at x equal to 0. There is no horizontal asymptote because as your numbers get larger going to infinity, the x blows up. Let's look at f of x equals natural log of 2x squared. Because of the x squared, I can put in negative numbers. Remember, the natural log function itself can't be negative or 0. I can put in a -1 because I square it first and then multiply by 2, so it's positive. The only thing I can't have here is that x cannot equal 0. I can't have x equal to 0. So we will have to look at numbers on both sides of 0. So let's think again about these asymptotes. For a vertical asymptote, we'll look at x equal to 0. And because we don't have the x multiplier for the vertical asymptote here, if you start plugging in numbers, you do see that you do have a vertical asymptote at x equal to 0. It does not approach 0. Your x values get bigger and bigger and bigger negative numbers because this is basically the same shape as ln of x. If the x's are positive numbers, it looks very similar to that. Horizontal asymptote, none. Again, if we plug in x's that get bigger and bigger and bigger, our values for the function get bigger. And if I plug in negative numbers, they also get bigger, but they don't approach anything. They continue to increase. So let's try the derivative of this one. Move on to derivatives. I don't need to do the product rule. There's no such thing as ln times 2x squared. This is inside the function. So remember the derivative rule for the natural log of x is 1 over x. We have to use the chain rule. It's 1 over u, which is 2x squared, multiplied by the derivative of 2x squared, which is 4x. You may need to use the chain rule in a number of problems like this. We can simplify this. The 2 and the 4 will cancel. I'll have 2. The x's cancel. I just have 2 over x. So that's a very neat little derivative. So now we set it equal to 0. And we find out that we don't have anything that's going to make this fraction 0. Remember that for a fraction, to get a 0, the numerator has to equal 0. And that can't happen. That's impossible. Okay? So there is no critical number when f prime of x equals 0. No critical number. But we also have to look and see f prime of x does not exist. And when a fraction does not exist, that means that the denominator equals 0. So for the 2 over x, that is true that the derivative does not exist. The denominator equals 0 there. So f prime of x does not exist at x equal to 0. Well, we already knew that. It's a vertical asymptote. But that means the graph is in two different places. So we do have to look at a number line and check to see what we get on either side of 0. If I plug in a negative number, f prime at -1, f prime is 2 over x. I get 2 over -1. I get a negative. I plug in a positive number. I get 2 over +1. I get a positive number. So my function f decreases on the left side of 0 and increases on the right side, but they're separates. They don't connect. It doesn't go down to 0 and back up. This is not a relative min. So this function, we say, decreases and then increases, but there's not a relative min at all. Let's see if I can put that up here. Okay. Decrease from -infinity to 0. Increase from 0 to +infinity. No relative min, or no relative extrema. So back over to the first derivative. Let's look at the second derivative. Have to take the derivative of 2 over x. The easiest way to do that, to rewrite it as 2 times x to the -1 power. -1 power. And use the power rule. So my second derivative is -2x to the -2. Remember when you subtract 1? So this is -2 over x squared. And the same type of thing happens. For our second derivative, it's never equal to 0 because the numerator is -2. You can't plug in an x to make it 0. But the second derivative does not exist at 0. So we have to do the same kind of thing that we did with the first derivative, with the second derivative, to determine concavity. So I use my number line at 0, and in the second derivative, let's see what happens at -1. Well, plug -1 in for the second derivative for x. I square it, I get 1. -2 over 1 is a negative. I take the second derivative at 1. I plug in 1, square it, I get 1. -2 over 1 is a negative. So this is concave down everywhere. Concave down. Problem is, I cannot go -infinity to infinity. I can't write it like that because there's an asymptote in the middle. So I say, concave down, -infinity to 0, and then again from 0 to infinity. So let's see if there's any way we can get this graphed. I know that I have a vertical asymptote at 0. So I know it's in two separate pieces. So let's think about, let's try intercept. Let's see what I get if I just plug in, not 0, excuse me. Yeah, I'm going to plug in a number. I want the function to equal 0. Let me do that up here. That's going to be a little bit longer. I can't plug in 0. That's the easy intercept. I can let the function equal 0. And I know that probably looks strange, and because when we did the e to the x's, it never equals 0. This does. Remember that this is base e, so I can make e to that power and e to that power. So 1 is equal to 2x squared. Kind of an odd thing to do. So my x squared is equal to 1/2. Take the square root of both sides. So x is approximately plus and minus the square root of a half, which is about 0.7. So I do have, f of plus and minus, what am I doing here? I don't want to do that. Plus and minus 0.7 equals 0. That tells me what I need to know. I let my original function equal 0. I solve for x, so that gives me my y, my x-intercepts. Okay? All right, back to my graph. I know that this thing right here is a vertical asymptote, right at 0. I know now that when y is equal to 0, it crosses at 0.7 and at negative 0.7. I know that it decreases on the left side and is concave down. So my function decreases, but it cups downward. And it approaches that as an asymptote. And on the right, it increases, but it's concave down. And since this is a squared, that gives you some symmetry. It really looks the same way. It's supposed to look the same way. So they both cup down, concave down, but there's no extremum, but you do have to separate to look at first derivative and second derivative, even if you don't have a max or a min, and there is no inflection point. No IP. In math, that's inflection point.